Okay, Algebra 2 fans, it's 4-5. We're talking about 2x2 matrices, determinants and inverses, all of 2x2 matrices. First of all, what's a square matrix? I think we talked about this in class, but a square matrix has the identical number of rows and columns. So if you have m rows, you would also have m columns. Okay, that's where it gets its name square matrix, is we're talking about same number of rows, same number of columns. Now, if you take the number 1 and you multiply it times a variable like x, what do you get? Don't you get x? Just like if you did like 1 times 2, you would get 2. So we use the number 1, and is called the multiplicative identity for multiplication. So the number 1 actually has a name for multiplication. It's called the multiplicative identity. Because when you multiply any number times 1, you get the same number you started with. It keeps the identity. That's why they call it that. Now, is there something like this in the form of a matrix? In other words, is there something called a multiplicative identity matrix? And we could call it matrix I. We could use the capital letter I for identity. So that when you take I and you multiply it times any other matrix, you get the same thing you started with. Whether you multiply, this would be considered multiplying on the left. This is multiplying on the right. Because remember, we talked about how matrix multiplication is not commutative. So, left and right. Well, there is such a matrix. For the 2x2 variety, this right here represents the identity matrix. How do you find the identity matrix? Well, it's got 1s along the main diagonal right here. This thing's called the main diagonal. That's from the upper left to the lower right. Okay, so main diagonal has 1s. Everything else is 0s. All others are 0s. So we can take that idea and we can extend it to 3x3 and 4x4 and 5x5 square matrices. The main diagonal contains all 1s. Every other entry is 0. That doesn't look too complicated when we're talking about a 2x2 matrix. Alright, so let's see. Let's do our matrix multiplication here. We got a 2x2 and a 2x2. First of all, can we do this? Yes, we can, because the inside dimensions are the same. Right? They are equal. That's the inside number rule. Well, the outside number rule tells me that the product will have dimensions 2 by 2. So when I get done with this, I'm going to have a 2x2 answer. Well, and we know that there's 4 entries in a 2x2. 1, 2, 3, 4 different numbers. So we're going to take row 1 times column 1, just like we did yesterday. Okay. First numbers together, so 1 times 3, that's 3. Slide. You'll notice that my left finger slid to the right and the pen slid down. So now I've got 0 times 5. So let's show that to you again. 3 times 1, 0 times 5. You must slide both on the left and the right each time. So 3 plus 0 makes 3. Move over to this column. 4 plus 0. 4 plus 0 makes 4. Slide down to this row. 0 plus 5. 0 plus 5, that makes 5. And 0 plus 6. 0 plus 6. you'll notice that the matrix did not change its identity. It stayed the same. That will happen the same way if you multiply it on the right side. So I just showed you how it works with the left, but it also works with the right. Okay? Got a question for you. Does matrix division exist? The answer to that is, the short answer is no. Matrix division does not exist. Okay? We will take a look at what does exist and what we're going to do to get rid of matrix multiplication, but it is not matrix division. There's no process called matrix division. All right, 2x equals 5. How do we handle 2x equals 5? How do we solve for x? Most of you are going to tell me that you're going to divide both sides by 2. But I'm going to say, well, can't we multiply by the reciprocal? I remember in middle school we said that about a billion times. Division is the same as multiplication by the reciprocal. Well, that's true. So we multiply here, we multiply there by half. Now what happens over here? You multiply 2 times a half. Don't tell me it disappears. It turns into the identity. Remember that? The number 1. Now I realize that 1 times x is still going to be x, and that my true answers are sitting over here, 2.5. So this process that's happening here is very important, but it's extremely boring. This is the interesting part, because the interesting part has the answer that we're looking for. So on the left side, really important stuff happened. Without that stuff, we wouldn't have an answer. But it's really boring, right? You multiply by 1/2, boom, it disappears, turns into the number 1. Okay, now, so is there a way that we could solve these two matrix equations? We have a matrix A times a matrix X equals the identity, or X times A equals the identity. Now, if those two are true, then X, it has some special properties. Because if you're multiplying A times some matrix and ending up with the identity, that must mean that there's a relationship between these two. In fact, the relationship between these two back here, lots of times we call them reciprocals, but another word we could use is they are inverses of each other. 1/2 and 2 are inverses. So these two would have to be inverses of each other. Otherwise, they wouldn't cancel out and become the identity matrix. So now, what kind of notation are we going to use? You're going to see notation in the book that says x equals a to the negative 1 power. That means A inverse. When you see that, that's how you're going to read it. A inverse. Okay. We know that matrix multiplication is not commutative. We need to be careful here. I'm supposed to solve this for x, and I have a simple equation, ax equals b. Now there is nothing called matrix division, which is what you guys all want to do with this question. Remember, we're solving for x. So here's what we have to do. We have to take the inverse and we have to multiply it on both sides. Now I want you to pay close attention to where I wrote the A inverse. I wrote it in front of the B. Yes, that's extremely important. Now, was it important up here? I wrote the 1/2 on the left and I wrote the other 1/2 on the right side of the 5. Did that make any bit of difference to my answer? The answer is no, it did not. But in multiplication is commutative. That means you could switch things around and it's okay, it's legal, it's legit. That's not true for matrices. So if you're trying to do the same thing on the left side of the equation as you're doing on the right side of the equation, then we need to be super careful. We need to do what's called left multiplying on both sides. Left multiplying on both sides. Now, so we have A inverse AX equals A inverse B. What do A inverse and A multiply together to give me? Well, they're inverses of each other. They're supposed to cancel out. A few seconds ago, we looked at something where it said if you multiply something times its inverse, you end up with the identity matrix. I know, it's really important but really boring. So it becomes the identity matrix. Well, what's the identity matrix times any other matrix? Just that matrix. So in other words, it looks like it just vanishes and disappears. So I've got X by itself, and on the other side is my answer. Yes, those are matrices. So we're going to have to figure out how to find an inverse because we're not going to be able to do it unless we know how. So let's talk about the steps of finding an inverse. How do we find an inverse? Well, you're going to see a matrix, and then when you see this little notation to the -1 power, it's saying find the inverse. Because that matrix to the -1 power is the inverse. Now we need something before we can go any further. We need something called the determinant. Okay, that's not the stuff you stick in the washing machine. Okay. We need to find that determinant. How do you find a determinant? Well, this is pretty easy, so follow along here. I take the product along the main diagonal. Product meaning multiplication. So -4 times 2 is -8. Typically what I do is I write it above the matrix. That way I don't mess up the order because it's important. And then I take 5 times -3 and I get -15. And we want to subtract. Okay, it's always subtraction, never addition. Now I realize for those of you who are out there, you're saying to me, well, wait a sec. Isn't subtracting a negative equal to adding a positive, right? Don't they just cancel out? The answer is yes. But if I say to you that we're adding them together, sometimes I get kids who think that we should just add them all the time, and that's not true. If subtracting a negative turns into a positive, that's a different story. So my determinant is equal to -8 plus 15, which gives me, what, 7? Now, you'll notice that I also wrote something else down here because we're going to do something with this determinant. It says multiply the new matrix by the reciprocal. Alright, so I'll start my new matrix down below. So that instruction right there says multiply the new matrix by the reciprocal. The reciprocal of 7 is 1 over 7. Okay? Now, the next two things you need to do. Switch the main diagonal elements. Switch the main diagonal elements so that -4 comes to the upper left and the 2 goes to the bottom right. The last step is that we multiply the other values in the matrix by -1. Now, that does not mean they switch places. They stay exactly where they are. So, this is going to stay where it's at, but it will turn to +3. This will stay where it's at, but it will turn to -5. So, +3, -5. Now, this whole thing is called the inverse. Now, could we write it like this? Could we write it as negative 4 over 7, 3 over 7, negative 5 over 7, 2 over 7? Could we write it like that? The answer is yes. That is also another way to write the inverse. I don't particularly like that form. And so you can leave your answer like this on a quiz or test if I just ask you for the inverse. And when we get to solving systems of equations using matrix multiplication, you need to look at it in this form. Look at it in this form.